Hello. The point of this video is to discuss somewhat finer details of the Galois correspondence. Which identifies two structures, lattice of subfields of a Galois extension on one side and then lattice of subgroups of the symmetry group of the extension but flipped. So we'll be looking at a specific path in this Galois subfield lattice and then this is Galois. Now I'll be interested in seeing when this leg is Galois. So E extending K is Galois. According to Galois correspondence, E is on the other side, on the lattice of subgroup, is the counterpart of the automorphisms group of F over E. And that is, of course, is a subgroup of automorphisms of F over the base. So the characterization of that extension being Galois is in terms of the subgroup, and it is simply for that subgroup to be normal. So that's what I'm going to argue for. That is a statement. And the argument is going to be rather long. And since I'm going to turn this Galois condition into some condition on groups, I'll have to look into groups a bit more. So let's look at what we have. So we have an intermediate subfield, and we can look at the full Galois group of F over K, and then we could look at those symmetries of F which not move E as a whole around. So they might move elements inside E, but just keep E as a subset fixed. So I will look at the collection of such. So phi of E as a subset is equal to E. Well, it's very straightforward to see that this is a subgroup. And I could look at what any such phi does inside E does to the elements of E. So that procedure is called restriction to E. And I will be seeing some automorphism of E, and hence an element of this group. And of course this restriction is a group homomorphism. Composition works accordingly with this restriction, so we can look at the kernel of this, and the kernel will be symmetries of F which do not move elements of E, and we call them automorphisms of F over E. So that is the kernel. And knowing the kernel of a homomorphism and knowing where the image is good for counting purposes, which we're going to do really soon. But before, let's look at this subgroup inside our automorphism group and characterize it in group theoretic terms. So I'm going to claim it to coincide with, in terms of this group, is the so-called normalizer in this group of this subgroup. So that is what this subgroup is really in terms of group theory. And that is because, basically because Galois correspondence, because E can be written as the subfield of invariance of automorphisms over E. So that is just Galois correspondence. And then if we take any symmetry from our group, from this large group, then if we assume that this is an element of a normalizer, so let's just characterize elements of a normalizer and see that they're exactly this. at this special automorphism. So what is to be in the normalizer is to not conjugate the subgroup f over e, symmetries f over e. So this conjugate with our chosen psi has to be just the subgroup we start with. So that is just being in the normalizer, that has been in here. And we want to argue that we have to have, our psi has to be in here. But why is that? So what we have to argue that psi is not moving E as a whole. So let's see what psi of E, which is another subfield of F, isomorphic to the image of an automorphism of a subfield will be another subfield. So let's take any element in this group and see it as a conjugate of something again in this group and in our psi, and let's apply it to this side. So what we have is psi of E, and then psi inverse, and then something which stabilizes C and then psi. So if you apply it to any element of this conjugate subfield, you will be still sitting in the conjugate subfield. So any element of our group, of this group, which is the same as this conjugate, will stabilize this field. But we know what stabilizes E, just this group. And so we are seeing that any element which stabilizes E stabilizes this. So they must be the same. So all this is to argue that this is sitting inside. Why the other way around? Why this subgroup is definitely a normalizer subgroup of this? Well, simply because this is a kernel, so it has to be normal. So that's a quick explanation of why we have an equation sign here. So another useful fact I'm going to employ is by looking at this embedding. So this is just going around the chain and noticing that the index of this embedding is the same as the index of as a degree of E over K. Well, that is because I can write this degree as a ratio of 2, the degree of F over K, so overall degree, and then the degree of F over E, right? So this degree times this degree is, the product of those is that degree, and I'm just rewriting the statement. But then using the Galois property of this extension and this extension, I can replace the top by the order of the large symmetry group of this one, and the bottom is the order of F of symmetries of F over E. And so that is the index, and hence the statement. So okay, now I'm ready to go about my characterization, go both ways. So if I will start, say, assuming that E is extending K in the Galois fashion, I have to argue that this subgroup is normal. Okay, what I know is again, I have to use the larger field. So I know that if I start with a Galois extension, then the way it sits inside any larger Galois extension has to be effectively unique. So the set of homomorphisms from E to F will have to be just acted upon freely by the group of symmetries of E. So effectively the set of subfields of isomorphism type E inside my F is just one point, because this set is the quotient set with respect to this action given by composition. So just one embedding. Okay, but let's look at this set of embeddings from a slightly different point of view. So on the set of embeddings, we have another action. We have we have the action of the symmetry group of F. Symmetry group of F, by this procedure, so taking symmetry and applying it to a subfield, will give us an isomorphic to E subfield. So we have an action of the automorphism group of F over K on this. And then we saw that our E as a sub field. So here we look at the elements of this set are subfields of F isomorphic to E. Isomorphism is supposed to preserve the scalars from the base K. So this set is acted upon by the symmetry group of the large field F, of course, by just permuting the subfields. And we could see what is the stabilizer of a given E, and that has to be this subgroup, right? Because they're just literally symmetries which do not shovel a chosen E, copy of E around. So we could be sure that that the quotient by this, and we identified it with a normalizer, so quotient by the, I will write it as a normalizer, is a part of it, is an orbit inside. But this is one element in the Galois case, so there is no space. That has to be just one element orbit. And so we see that there is no difference between these two groups. They will have to be the same in the Galois case. In the Galois case, this just go together into the same thing. And so what we have finally is the following. So we have our group, and we have this being normal in it. Just what we wanted. Okay, one direction is good, so then look at the opposite direction. Let's assume that the subgroup of symmetries over E is normal. Then we have some estimate for the size of the image. So the size of the image will be the index of this inside what we quotient by to get the image. So the image of this restriction, which is a subgroup of the symmetry group of E, and it is well bounded by the index of this group inside this group, and this index is bounded from so assume that it is normal, so we know that this is the same as that, so this index is just this index which we identified with the index of K and E. So that is in the assumption of normality, that is equal to the order of the image. And since it is a subgroup, it's bounding from below the order of the symmetry group of F. But we know that the symmetry group of F cannot possibly be larger in size than this. So the only option is that they coincide. That is the Galois condition. E over K is Galois. And now we are done. So now we have this complete characterization of when an intermediate subfield is a Galois extension of the base. It's if and only if the corresponding subgroup, the subgroup which fixes it inside the larger Galois extension, is normal. I will stop here. See you later.